I want to provide some basic intuition behind the concept of renormalization in physics, which is fundamental in the study of particle physics, and not just that. The basic idea is to consider the action. We know that the action is essential in classical physics because it helps us understand what the laws of motions are, so we can derive the laws of motions from the classical action. And if we want to move from classical physics to quantum physics, basically we start from the classical action and then we define the so-called path integral, which is a generalization to quantum mechanics of the action. So we have an integral, a complicated integral over some measure, which is related to the field. Let's call the field chi. Then here we have the exponential e to the I, the action divided by h bar. Now, let's assume that we can simplify our units in such a way that h bar is equal to 1, therefore it does not appear here, and also the speed of light is equal to 1. This basically means, for example, that length is equal to time, because if the speed of light is equal to 1, it means that it is dimensionless, and therefore, since the velocity is a length divided by a time, it means that length has the same units as time. So we can say that length is equal to time for simplicity. And what does h bar equal to 1 mean? It means that since h bar is energy times time, it means that energy, let's call it E, capital E, is equal to time inverse, which is also equal to length inverse, so 1 over length. Energy is 1 over length, right? And in the action, so if in the action we have a kinetic term of the kind d mu chi, usually in the action we have such a term which is not multiplied by any other terms, by any other constants. We might have a factor of 1/2, but we have numbers, so it means that this term here appears in the action. So the action is an integral over our d dimensions. So let's say that it's an integral over d dx. Basically we have x1, x2, xd coordinates. We are in a d-dimensional space, and here we have 1/2 d mu chi plus other terms. Since the action is dimensionless, because the action is measured in terms of h bar, in units of h bar, so h bar is an action, energy times time, where energy is measured in terms of length to the -1. It means that since we have two partial derivatives here, these are, of course, length to the -2, we also have this term, which is length to the power d. So we have length to the power d -2, and then we have two fields. So the unit of chi squared, this should be dimensionless because it is equal to the action. So this should be 1 if you want, which means that the field is measured in units of length to the power 2 minus d divided by 2, because we have chi squared, so chi is measured in these units here if we use length as the basic unit. This is just some basic considerations that we have to keep in mind for the other part of this video. But now let me return to the path integral here. So let me rewrite it by canceling what I have written so far, because I want to clean the whiteboard. So I have an integral of the kind d chi e to the is. The action, in this case, I will think of the action as a field such that the field is given by a sum of two fields, phi plus chi. Why am I doing so? Now, this summation here, you can think that this is another field, capital Phi, for example, which is given by phi plus chi. I have split the field in two parts, where phi, lowercase phi, is the low energy part, whereas chi is the high energy part. What does it mean? Well, if you think of the field as given by modes, of course, you have low energy modes and high energy modes. If you think about the Fourier transform, for example, it splits the signal in modes. So we have the low energy mode and the modes and the high energy modes. And in the path integral, we can integrate out, for example, the high energy modes. So what we are left with is a so-called effective action. So I can define this to be an exponential e to the I sf, where f stands for effective, which depends only on the low energy modes of the overall field phi plus chi. So you can understand that when we have a path integral, we can integrate the high energy modes, and what we see is the effective action. So from the effective action, we have a theory which holds only in a certain range of energies, because we have integrated out the high energy modes. So we can go, for example, from 0 to some energy lambda. And we have integrated out chi, which maybe was defined between the energies lambda and lambda plus a certain increment delta lambda. So these are the high energy modes that we have integrated out from the path integral, and from this action we obtain an effective action which holds only in this range of energy. So you can think of this as a so-called renormalization group, where by performing the integral over high energy modes we change the scale of our theory. This is how we can express in words what we have written down in terms of these equations here. So in physics, there are several theories that hold only in a certain range of energies, because, for example, when we use the theory, when we try to apply the theory to a range of energies higher than expected, we get wrong results. And this is due to the fact that our theory is indeed an effective, is given by an effective action, because we don't have the original action, we only witness the low energy action. So these are just informal ways of expressing this. And now I will continue to describe what we can obtain with this effective action. In general, we will see that the effective action contains some corrections, some quantum corrections to the coefficients that appear in the action. In particular, we will express this action as a kinetic term plus a potential. So we have something like 1/2 d mu, and then here we have a field phi, d mu phi plus some potential. Now we will see in this video that when we change the scale of our theory, this potential here that we will express in terms of powers of this field, so it's as if we express this in a series, we will see that when we change the scale, there will be corrections to the coefficients that appear in the potential. So those coefficients are also known as the couplings, and these couplings are not really constants when we change the scale of our theory. So they will be functions of the energy scale, and they will be renormalized. So I want to show you the idea behind this. Despite it's a complicated concept, I will try to simplify the reasoning and the steps to show you mathematically that we have corrections to take into account. So let's start from here. In this video, I want to show you an example of renormalization of the coupling constants, the so-called coupling constants that at the end of the day are not really constants. In particular, we start from a field phi of x. X belongs to Rd, so we are in d dimensions, and a generic action can be written in the following form. So we write S sub lambda. Lambda describes the energy scale. So it's the energy scale that we are interested in. It's lambda. And we have also another superscript here, which is F, which stands for effective. So this is the effective action. That means that, for example, we have integrated out other fields. So the only field that we are going to consider is phi, but maybe we have integrated out other fields, so we don't see those fields, we only see phi. And we are interested in the energies that go from 0 to lambda. So in principle, phi contains all the energy from 0 to this capital lambda here. This is equal to integral d dx. Then we have 1/2 d mu phi that in the following we'll also, so we will also write d mu phi as d phi squared for convenience. And then here we have a potential term v of phi. So we write the action like this. Now, for simplicity, we choose v of phi such that this is equal to v of minus phi. So there is some symmetry in the potential. And we can write v of phi in terms of dimensionless coupling constants. Couplings, let's say, because they will not be constants anymore. We will show it at the end of this video, but at the moment we are assuming that the constants are g2k. So these couplings, d2k, at the moment they are constant. And the potential v of phi can be written as summation over k from 1 to infinity lambda to the power d minus k d minus 2 d2k divided by 2k factorial phi to the power 2k. Now first let me explain the presence of this part, so of this power here. So if you check the dimension of phi to the power 2k, this has dimensions of lambda to the k d minus 2, right? Because the field phi is a length to the power 2 minus d over 2. But length is lambda to the minus 1. So this is lambda to the d minus 2 over 2, because lambda is energy. Energy is length to the minus 1 in the units that we are considering, where h bar is equal to 1, the speed of light is equal to 1. So this is usually done in quantum field theory. And therefore, phi squared would be lambda to the d minus 2. If we raise it to the power k as well, so we get d minus 2 times k, which is exactly this. Therefore, this, I mean, the units of this would simplify this part, and we are left with lambda to the power d. And lambda to the power d is necessary because remember that the action should be dimensionless. It should be dimensionless because we have set h bar equal to 1. So h bar as units of action. So if h bar is dimensionless and it is equal to 1, therefore the action here should be dimensionless as well. But remember that in the integral we also have d dx. So this is length to the power d, length to the power d, which is lambda to the power minus d. So this lambda to the power minus d will cancel this lambda to the power d. So this is the reason why you see such a factor. Because remember that these couplings here are dimensionless. Now notice the fact that phi is raised to an even power. So why is it even? Well, it's even because it's very simple. We have chosen the potential to be symmetric. So there is some symmetry in the potential. this symmetry here, and therefore we cannot have odd powers of phi. And also, let me point out why there are no derivative terms, because in principle this potential could also contain derivatives of phi, right? Except for possibly this derivative here, which is the kinetic term, and the kinetic term is usually put outside of the potential for the sake of convenience. So this is the kinetic part of the action. But anyway, we don't have those terms because the derivatives of phi would affect the high energy modes, right? So if we take higher order derivatives of phi, we are just going to emphasize the high energy modes. And if we are interested in the low energy modes, it makes sense that we can disregard high derivative terms. So this is the assumption that we make, that v of phi has this form, so that we can neglect, in principle, higher order terms for the derivatives. And also there is some symmetry in the potential, which is this kind of symmetry here. Now we are going to write the field phi in the following form: capital Phi plus chi, where capital Phi here will contain only low energy modes, whereas capital chi, or just chi, let's call it chi, and in the following I will also call this phi, but if there is no ambiguity, I will not point out the fact that this is different from this. But if in case there is any ambiguity, of course, I will say that this is capital Phi and this is lowercase phi. So please do not get confused. Anyway, here, this, as I said, this capital Phi contains only low energy modes, and chi will contain only high energy modes. Now, we have to substitute it in the action. So this will have to be substituted in the potential and also in this kinetic part. So the kinetic part will be quite simple. In particular, d lowercase phi squared will be written as d capital Phi squared plus d capital Chi squared. And in principle, we also have cross terms, right? Terms that are proportional to d phi, d chi. But let me tell you that such a term will not appear in the action, and this is because phi is a low energy, the low energy part. So this is relatively constant with respect to the chi, which oscillates more rapidly. So we assume that when we integrate over d chi, or actually over d dx, we only have to integrate over this term, which is the high energy part. But since it oscillates very rapidly, we assume that those oscillations, when you integrate them, they will give a zero result. So we will neglect such a term. For example, we could also neglect cross terms of the following kind. So phi times chi, for example. So this is not something that will appear in the action, because when we integrate it, phi, capital Phi, is relatively constant with respect to chi, so we integrate over chi, but this is the energy part that oscillates very rapidly, so when we integrate it, this will give us a zero result. So all in all, the kinetic part will transform like this, and therefore the effective action at scale lambda of capital Phi plus chi, which is just phi, remember that, this is equal to integral d dx. Then we have 1/2 d capital Phi squared plus 1/2 d chi squared. And then we also have the potential term, which is v of phi, capital Phi, plus chi, like this. Now we are going to expand this v of phi plus chi in a series, in particular in a series over chi. So this will be v of phi. We are going to expand it near, so we are near chi equal to 0. So we have v of phi plus v prime of phi times chi plus v double prime of phi times chi squared over 2 factorial plus higher order terms. Now we can choose a capital phi such that v of phi is minimum. So this means that we can choose phi such that v prime of phi is equal to 0. So this term here will be 0. And this can be done because we can always add a constant to phi such that v prime of phi plus constant, this is 0. And a constant does not affect the low energy mode, so we are not changing the physics. Even if we translate phi by means of this constant, we are just going to add a low energy part, and we are not changing the actual behavior, the actual physics that we are considering. So basically, this says that we can set this term here equal to 0. And then here, in principle, we have higher order terms. But if we consider only one loop diagrams, we can truncate this series here. So basically, this is the last term that we are going to consider. We are going to truncate the series here. So this is the last term. And therefore, we can write the action as f sub lambda of phi plus chi as integral d dx 1/2 d capital phi squared plus v of phi. This v of phi here simply comes from this part of the potential. And then I have plus integral d dx 1/2 d chi squared plus 1/2 chi squared v double prime of phi. And then, as I said, we're going to truncate it like this. Now we define this part of the action as sf lambda of phi, capital Phi. You can see that here we don't have the presence of chi, so this is exactly sf lambda of phi. And therefore we can also define the variation of s lambda, so the change of s lambda f of phi. So we define this to be sf lambda of phi plus chi minus s lambda f of phi. And at this point we are going to lower the energy scale infinitesimally by integrating out chi over the range of energy lambda minus delta lambda lambda. So basically we are choosing chi so that it contains energies only in this range from lambda to lambda minus delta lambda. Remember that our initial action contains basically all the energies in the interval 0 lambda. At least in principle it contains all the energies in this interval here, whereas chi only contains energies in this interval here. So we can write e to the minus change in the action s sub lambda f of phi. This is equal to, we have to integrate out over chi, and then we have e to the minus integral d dx, and then we have 1/2 d chi squared plus 1/2 chi squared v double prime of phi, like this. Now we go to the Fourier domain. In particular, we are going to rewrite, for example, integral d dx d chi squared. We are going to write chi by using the Fourier transform. So we have integral d dq q pi to the d, d dp 2 pi to the power d, then we also have to integrate over d dx. Then we have iq times ip. These terms come from the derivative, and when you take the derivative, you're going to take the derivative of the complex exponential that I'm going to write down in a moment. Here you have the dot product, so basically this is I q mu times I p mu, like this, if you want to interpret it. Then you have chi hat, the transform, which depends on q. Then you have chi hat of p. And finally, you have the complex exponential e to the I p plus q dot x. Now you can integrate over x, and then you can also integrate over q. And when you do that, you have integral d dp divided by 2 pi to the d chi hat of p chi hat of minus p times p squared. Similarly, here you also have another integral. You have the integral of d dx chi squared v double prime of phi. Now we are going to assume for simplicity now that v double prime of phi is relatively constant over space with respect to chi squared. Later we will be more general and we will consider v double prime of phi as a function of x, so it can indeed vary over space, but for now let's consider it to be a constant. So this is approximately equal to v double prime of phi, and then we have integral d dp, so I'm using the Fourier representation of chi here, so we have d dp divided by 2 pi to the power d, then we have chi hat of p, chi hat of minus p, like this. So the integral over chi, this integral here, becomes the following. So we have integral d chi hat, so this measure here should be interpreted like this. It is proportional to d chi hat p1 over 2 pi to the power d. Then we have d chi hat p2 divided by 2 pi to the power d dot 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 d chi hat pn divided by 2 pi to the power d. So we are assuming that we have n modes, and you can understand that this n actually goes to infinity. So this measure here is not rigorously written, at least in a mathematical way. But we are going to rewrite this n in another fashion in a moment, so just give me a few minutes. We're going to rewrite this n, but for now let's assume that we have n modes. So here we have the exponential of minus 1/2 integral d dp divided by 2 pi to the power d. We have p squared plus v double prime of phi, chi hat of p, chi hat of minus p. And this here is just the mode of chi hat of p squared, assuming that we indeed started from real fields. So chi is a real quantity, therefore here chi hat of p is the complex conjugate of chi hat of minus p. So we get mode of chi hat of p squared. Now remember also the fact that we are integrating out chi, and chi contains energies in the range lambda minus delta lambda lambda. So it means that this p squared here is approximately equal to lambda squared, because this is a narrow band. So it means basically that since delta lambda is very small, p squared is approximately equal to lambda squared. And the integral here is just a Gaussian integral if you think about it, with n modes. So this will be proportional. This will be proportional to 2 pi to the power n over 2, and then we have lambda squared plus v double prime of phi to the power minus n over 2. We can also rewrite this as e to the n over 2 natural log of 2 pi minus n over 2 natural log of lambda squared plus b double prime of phi, like this. Now, this first part is not really important because this is just a constant in the action, and these constant terms do not affect the physics. They are not important, we can discard them. So this is something that can be discarded. This is actually the important part. So is the important part, and also remember that this n, this capital N, goes to infinity, but we have to find another way to write it. In particular, if we place our theory in a box with the linear size L, our momentum would be discrete. In particular, P mu would be discretized like this, 2 pi, then we have n mu, which is an integer, and mu is an integer, divided by capital L, the size, the linear size of the box. The volume that is occupied by one mode in momentum space is delta P1 times delta P2 dot 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 delta Pn. It is just equal to 2 pi over L to the power d. Whereas the total volume that we have in momentum space is the integral over d dp. And remember that we have to integrate over the energies, let's call them mod p, less than or equal to lambda, greater than or equal to lambda minus delta lambda. So we are assuming that our momentum is in this interval here. The mode of our momentum is contained in this interval. If we go to spherical coordinates in d dimensions, this is lambda to the d minus 1 times delta lambda. So this first part comes from the fact that this interval here is very small. So when we go to spherical coordinates, we have this first part, lambda to the d minus 1, multiplied by delta lambda, which is the length of our interval here. And then we have integral over the solid angle, d omega, in d dimensions. We have to integrate over s d minus 1. Let me explain what this s d minus 1 is. This s d minus 1 is the surface of the sphere in d dimensions. So the sphere is d-dimensional. In particular, the volume of the sphere is d-dimensional, but we have to integrate over the solid angle, which means that it's as if we are integrating over the surface of the sphere. But the surface of the sphere is d minus 1 dimensional. And this can be evaluated, but we are not really interested in doing so now. You have to use just the spherical coordinates in d dimensions, and this integral can actually be carried out. And you will find some gamma functions and so on that I don't want to write down now. So this is equal to, let's define it like this. So we have lambda d minus 1 to the d minus 1 delta lambda, and then instead of writing this integral here, I'm going to write vol s d minus 1. So this is just notation. Now, the number of modes n is therefore equal to the total volume in momentum space divided by the volume occupied by one mode. The total volume in momentum space, we have just found it, lambda to the d minus 1 delta lambda vol s d minus 1. We have to divide by 2 pi divided by L to the power d. So in this case, we can write our delta S, so the variation of the action, the effective action sub lambda of phi, it can simply be written as, so we are just focused on, so remember where we started. We started from, where is it? We started from here, and we found that this is proportional, so there are some constants in the proportionality that we will disregard. So we found that that is proportional to this. We disregard the constants, in the constant part is not relevant in the action, and therefore the action is equal to this part here, right? So we have found how to express n Therefore, we can write delta S lambda f as n is lambda to the power d minus 1 delta lambda vol sd minus 1 L to the power d, and then we divide by 2 pi to the power d. We also have a factor of 1/2, and then we have the natural log of phi squared plus b double prime of phi. Now, instead of writing L to the power d natural log of lambda squared plus b double prime of phi, since we want to let L go to infinity, if we leave the expression like this will be divergent. But it is a smart thing to replace this by the integral over d dx, now assuming that the natural log can vary in space, so in particular this part of the natural logarithm, so this potential here, the second derivative of the potential, in this case is not a constant anymore, but we are going to integrate it over space. So we have the natural log of lambda squared plus b double prime of phi, like this. And once we do so, we can rewrite the variation of the effective action in the following way. So we have a constant that we can define as A, and in particular A is equal to, we define it to be the vol of Sd minus 1 divided by 2 pi to the power d. Then we have lambda to the d minus 1 delta lambda integral d dx natural log of lambda squared plus b double prime of phi. So I've simply rewritten the expression by writing down this constant, and then I have replaced this expression with this expression here, as you can see. So basically we have found that delta S lambda f divided by delta lambda of phi is equal to integral d dx a lambda to the power d minus 1 natural log of lambda squared plus v double prime of phi. And now let's consider this left part of the equation. This left part of the equation, if you remember the definition of delta S lambda f, this is S lambda f of phi plus chi minus S lambda f of phi. We have to divide by delta lambda, but delta lambda can also be written as lambda minus delta lambda. So this is the energy that we have when we integrate out chi, and this is the energy before we integrate it out. The energy that we have here when the action was written like this was lambda. So this was the scale related to this action, and then this is the final action that we have once we integrate out this chi. So the way that we have to interpret this ratio, so this is related to the derivative of the action with respect to lambda, but we have to be careful and pay attention to the sign, because this is not exactly the derivative of S lambda f with respect to lambda. Actually, we have to put a minus. This minus sign is necessary because we are lowering the energy scale. Remember that we are lowering it. So we start from the action, and then we lower the energy, and therefore when we consider partial derivatives with respect to lambda, we have to put a minus sign here. This is our starting action, and then we lower the energy. So that's why we get this. And now another thing that we are going to do is we are going to expand this natural logarithm in powers of pi, and in particular this can be written as a series, so we sum from k equal to 0 to infinity, and then we are considering the even powers of, even derivatives, d2k, d phi 2k. Now I will explain why we have even powers of these derivatives. we have to take the derivatives of the natural log of lambda squared plus v double prime of phi. We have to evaluate these derivatives at phi equal to 0, and then we have capital Phi to the power 2k divided by 2k factorial. Now, why do we have even powers of these derivatives and also these fields? Well, it's quite simple because v of phi, remember, v of phi is symmetric. V of phi is equal to v of minus phi. Therefore, also the second derivative v of phi is equal to the second derivative of minus phi, like this. And for example, the first derivative would be an odd function, would be minus v prime of minus phi, if you want. But the second derivative has the same property, therefore it should contain only even powers of these fields. So even if you write the odd powers, you will see that they vanish. Therefore, this is how we can write the expansion of this natural logarithm. Another thing that I want you to notice is that this series starts at k equal to 0. When k is equal to 0, here this derivative is just the identity operator. And here we get 1, here we get 1 from the factorial. And here, if you set phi equal to 0 in this v double prime, you get a constant here, and you get lambda squared here, so you get a constant. You get a term that does not depend, in any case, on the field. So that's a constant term in the action that we can disregard. In particular, we can start from k equal to 1, because as I said, we are neglecting the constant terms in the action. So we have found the following. So minus, I'm going to multiply the equations by lambda, the equation that we found. We have the derivative of s lambda f with respect to lambda. This depends on the field phi. We can write it as integral d dx. We have the series over k from 1 to infinity. And then we have, I'm going to write it like this, lambda to the power d minus k d minus 2. And then here I have lambda to the power k d minus 2 a. I have these derivatives d2k d phi 2k of the natural log of lambda squared plus v double prime of phi. Remember that I have to evaluate these derivatives at phi equal to 0. And also let me thicken my pen after zooming out. And then here when I close the parentheses, I have phi to the power 2k divided by 2k factorial, like this. This is what we have. So I have simply rewritten this, where is it? This equation here. After the considerations that we did, we can write it like this. I multiplied both sides by lambda, so you will find one more power of lambda here. And for convenience, I have also inserted this lambda to the power k times d minus 2. And of course, here I have to cancel that. So I have minus k times d minus 2. But now we can also find another way of writing this expression here, in particular minus lambda derivative s lambda f d lambda of phi. This can also be written as integral minus d dx, and here I have lambda. I have to take the derivative of, let's call it Vf, so the effective potential of phi with respect to lambda. In particular, in this case, we also have the kinetic term inside the action, but the kinetic term does not depend on lambda. So it does not depend on lambda. In principle, the kinetic term could also receive a quantum correction, but in this case, it does not receive any quantum correction. Only the coefficients g2k receive a quantum correction, as we will see shortly. And what is Vf? Well, it is exactly the potential that we wrote at the beginning of this lecture, in particular V of phi, remember. So now let's put F, but V of phi was equal to a series over k from 1 to infinity, lambda to the power d minus k d minus 2 g2k divided by 2k factorial phi to the 2k. At the beginning of the lecture, we had to think of this g2k as constants before integrating out chi. But after we integrate out chi, this g2k here receive some quantum corrections. So now we have to think of this g2k as a function of lambda. So basically we have to take the derivative of df with respect to lambda and insert the expression in here. This is quite straightforward because this is equal to integral d dx, and let's put the minus sign here. We also have the minus sign, then we have a summation over k from 1 to infinity, lambda to the power d minus k d minus 2, and then we have d minus k times d minus 2, which multiplies g2k, which in this case, remember, it depends on lambda. So we also get another term that is the following. In particular, the term is lambda dg2k d lambda, and finally we have phi to the power 2k divided by 2k factorial. Now you can see that it's quite long, but basically the idea is that now we have to equate this to this, because the left hand side is the same, is exactly the same. So we find a condition, a differential equation, let's say, for the coefficients. And in particular, we find the following. We find that lambda times the derivative of d2k d lambda should be equal to k times d minus 2 minus d2k minus a lambda to the power k d minus 2 second derivative 2k with respect to phi 2k natural log of lambda squared plus v double prime of phi, and then we have to evaluate this derivative at phi equal to 0. And this is the condition on the running of the couplings. So this is how the couplings run, quote unquote run. So this is how they change. For example, let's consider k equal to 1. For k equal to 1, we have to evaluate this derivative. It will be a second derivative when k is equal to 1, the second derivative with respect to phi squared, natural log of lambda squared plus v double prime of phi. Then we have to evaluate this as at phi equal to 0. Now, when we take the first derivative, we get v triple prime of phi divided by lambda squared plus v double prime of phi, and then after we take this derivative we have to set phi equal to 0. Now v triple prime, when we set phi equal to 0, this will be equal to 0. It's easy to see because v is an even function, so it contains even powers of phi. So when we take the third derivative, we're going to get a function that contains odd powers of phi. So when we set phi equal to 0, this will vanish. This means that the only non-zero term when we take this derivative will be the fourth derivative of v of phi. This is a fourth, so the fourth derivative. I could also indicate it, for example, like this, without these Roman symbols. I have v4, so it's the fourth derivative, and then I have lambda squared plus the second derivative of v of phi. And then I have to set phi equal to 0. Now this is quite simple to calculate. The fourth derivative will give me g4 lambda to the power d minus 2 d minus 2. Now pay attention that when we calculate the derivatives of v of phi, in this case this v of phi is the initial potential that we had in our theory, so v of phi is not v effective. In this case we have to treat these quantities, d2k's, these couplings, as constants. So the fourth derivative evaluated at phi equal to 0 is this, and then we divide by lambda squared plus the second derivative evaluated at phi equal to 0. What we get is g2 lambda squared. So all in all, you get lambda to the 2 minus d, g4 divided by 1 plus g2. Remember that this term here should be multiplied by this when k is equal to 1. So it should be multiplied by lambda to the d minus 2, which will cancel this term. So basically, what we get for k equal to 1 is d minus 2 minus d, which is just minus 2. So we get lambda derivative of g2 with respect to lambda equal to minus 2 g2 minus a g4 divided by 1 plus g2. So basically you can see that this quantity on the left, which is defined as the beta function beta 2, depends on not just the coefficient g2 but also on the coefficient g4. You would find that for the other beta functions, for example beta 4, there will be a dependence on other couplings. For example, beta 4 would depend on G2, G4, and G6, and so on.